Introduction, and thank you to the organisers for giving me the after lunch slot where everyone can drift off to sleep. No, wait, I am one of the organisers. Okay, so I have an abstract in. I'm going to talk about semi-implicit well, not so much the integration schemes, but as a consequence of using semi-implicit time integration schemes, we need to do a global matrix inversion of some kind, and then we need a linear solver, and that's got to run on the supercomputer, and they've got to run fast. And so this is a talk about how a couple of methods we might do to make our solvers go quickly. I realised that in fact I've got solvers in two different models, so I've got a tale of two solvers, which is the same joke that David made. David did it better, so. So there we go. So apologies for to answer David because he's already made the joke and it was better. Anyway, so I've got a paper out on mixed precision arithmetic in the endgame dynamical core of the unified model. That's work with David Walters, and then we've got a not quite ready to put the paper out performance of multigrid solvers for a mixed finite element dynamical core in Elfric, and that's with Tom Melvin and Eike Müller, which is hopefully going to come out soon. So for the numerical solvers, we have to do think about accuracy and precision. Of course, and they're not the same thing. So numerical algorithms have a defined accuracy, how fast they converge. In our case, to the continuous differential equations that we're replacing with these numerical methods. But computers themselves use floating point arithmetic to do that. And they have variable accuracy compared to real numbers. They're not real numbers. They're not they're not associative, and so you can have something called an accumulated round-off error. If you use a higher precision or more precision, you have a bigger data type, and that costs more energy and time to move around in the computer, although it might be more precise. But precision is not the same as accuracy. So this is a quote from John Gustafsson, who has various talks about what you could do instead of floating point numbers. But I've just taken this because it's a good example. So pi is 3.14 with a load of zeros and 1. That's very precise, but it's not very accurate because it's wrong. Whereas pi is between 3 and 4 is accurate, but it's not precise. Most scientific applications, especially weather and climate, use 64-bit arithmetic pretty much everywhere, kind of to avoid the accumulated round-off because people feel that we are very sensitive to error. But is this necessary? 32-bit, for example, is much faster. In a CPU, you get much better use of memory and cache if your data type is smaller. And on a GPU and some of the other processors, we now have hardware support for lower precision. And so you could use those to make our code go faster. Okay, so with these semi-implicit schemes, so in particular the Met Office unified model, the grid is a long lat grid, and it has a polar singularity. So near the poles, the grid points are very close together, and an explicit time-stepping scheme would result in an unfeasibly short time step for NWP. And so these more complicated semi-implicit time-stepping schemes are then constructed that treat the fast acoustic gravity modes implicitly, and then with things like doing semi-Lagrangian advection around, then this allows a stable integration around this polar singularity, so your model is then still stable. And the idea is you want to try and get long time steps. The time steps themselves are computationally much more expensive than for an explicit scheme, but the idea is you can take a much longer time step. To do that, you have to do the global matrix inversion. Okay, so here's a schematic diagram of what goes into the unified model endgame time step. So you have like slow physics and then this double looping where we do twice vection and fast physics, and then inside the inner loop, the Helmholtz solver itself, and then we update the residuals. Okay, so we're going to do the solve multiple times per time step. Okay, so at least 4. Okay, so the Helmholtz solve is actually just for the pressure correction itself. So the equation takes the form AX equals B. It's a classic large sparse matrix where B contains the forcing terms. So in operations at the Met Office at the moment, an N1280 long lat mesh has about 10 kilometers resolution at mid latitudes. So that's about 350 million grid points. So that's the size of the system we've got to solve. So for semi-implicit time-stepping scheme, the solver is part of a much larger nonlinear system solver procedure, and the accuracy of that solve is dictated by the stability of the time-stepping scheme. So we want the time-stepping scheme to be stable, so we only do the solve sufficiently accurately that the time step is stable. And in the Met Office unified model, it's a finite difference model, and so, for example, the pressure gradient is at best second order, so there's a limit to the effect of the accuracy of solving on the pressure. In other words, once the solver error is sufficiently small enough, other errors in the model dominate, like the discretization term, so there's no point in solving more accurately than that because it doesn't help you. So once we are sufficiently accurate that we are stable, then we're good. Okay, so here is post-condition by CG stab, which if you know Krylov subspace solvers you'll be familiar with, and if you don't, okay, don't worry. However, the point is there's a stopping criteria. When do we stop with a Krylov subspace solver? It's when we get to, so we have a thing called the residual vector, which is given by this expression for R here, the norm residual vector, and we stop when it's small enough. Now, if small enough is much bigger than, say, machine precision, in this case in 32-bit, where 32-bit, the unit of least precision is about 10 to the minus 7, then 32-bit arithmetic is sufficient for that. 64-bit arithmetic won't improve the accuracy of that solution at all if our stopping criteria is much bigger than that. And as I've just tried to describe or motivate, we don't need to solve very accurately. So typically we might solve to 10 to the minus 3 or 10 to the minus 4, which is way bigger than 10 to the minus 7. So we really don't gain very much by doing anything, by doing the solver in 64-bit. So we can do it in 32-bit. Okay, so we tried this with an idealized solver. It's a toy model to start with. This looks at the effect of convergence on precision. So we looked at the residual vector in 32-bit, 64-bit, and 128-bit arithmetic. Okay, so here it is. You can see the value of the residual falls as we do more iterations, as you might expect. The double and quadruple precision stay close together. Eventually, they start coming apart way down here somewhere. But the point is, single precision does take longer, but 10 to the minus 3, 10 to the minus 4, they're still very close together. But why are they not actually the same? There's a gap. There's a 32-bit takes more iterations, so I'm saying this is the iteration gap. So why is there a gap? Now, I claim it's because of loss of orthogonality of your Krylov subspace. So the Krylov subspace is the span of the vectors that you make by applying the matrix that you want to solve for repeatedly to the vector, and that's how we construct a Krylov subspace solver. Typically, we use the first two, which is then the vector and then the matrix times the vector, and we already use those in the algorithm. So to see if they're orthogonal, we just dot them together. Okay, so we could do that, and we could see what the answer would be, and then we could look at see how far away they are, see how orthogonal they are. So if we pretended that 128-bit arithmetic is truth, which it isn't, but it has smaller accumulated round off, then we can look at the difference for this orthogonality constraint. So because it's by CG stab, there are two Krylov subspaces, so that's the top and the bottom. So when we start with, the spaces are orthogonal, so that orthogonality measure is 0. And as we go through the iterations, because we're updating, the algorithm updates the Krylov subspace, it doesn't recalculate them, it updates them at each iteration, then we start to lose orthogonality, which is what we can see here. So in dashed red line is the red for the 32-bit arithmetic, and in yellow is the double precision. And okay, so I'm claiming, and I think you can see that the 32-bit comes away from 0 faster and converges towards 1 quicker. So the 32-bit loses orthogonality faster than the 64-bit, which is what our intuition might tell us. So that's why we end up with this iteration count. However, we can still do the solve. Okay, so this is why this is taking longer, but it's only taking a couple more iterations at the kind of accuracy we need to solve to, and 32-bit arithmetic is going to be much faster. Okay, so let's do it in the real thing. So this is actually running a mixed precision solver in the unified model. The solver, as I said, the solver is implemented in mixed precision. The pressure field was kept in 64-bit the whole time, with 32-bit increments to it, mostly due to the ease of interfacing with the rest of the model rather than for anything else, but it just means it's easy to make it work. So this is looking at then 11 different operational configurations. It's the first time step, the first solve, so that each of those start at exactly the same point, running on 96 nodes of a Cray XC40 at the Met Office. And you can see the fall in the residual. The blue and the red, they're pretty close together the whole time. BiCG stab's not guaranteed to be monotonic convergent, so you can see you get these jumps sometimes. So in 32, in the double precision compared to the mixed precisions are almost twice as fast. Okay, so that's great. So we like that. So that's the good news. That's a really good story, and this is why the Met Office is doing this in operations, because it's just basically a free win. We can do the solve in mixed precision and make the whole thing go twice as fast. Excellent, great. Are we done? Not quite. So I know it's after lunch. If you're a little bit squeamish, look away now. When does it break? Okay, so let's keep going and see when it breaks. So watching BiCG stab break is never pretty, okay? So let's go further. Let's see how far we can do it before it falls over. So let's go to 10 to the minus 5. And now we're seeing hundreds of iterations, okay? Now, hundreds of iterations are completely unaffordable for an operational model. And so we're stopping here, not down here, but down here is terrifyingly close to over here. And you can see these big jumps in the value of the residual. Its BiCG stab is breaking down. The mixed precision in red fares worse than the double precision. It sometimes actually fails, but even so, the double precision is not really looking very pretty, and so that's not very nice at all. Okay, so, and in fact, we have seen occasional problems even solving at 10 to the minus 4, typically with slow convergence for a particular configuration running, and then even failures where, because basically we're trying to divide by a near zero. It's the scalars in BiCG stab which are going to zero, and that's symptomatic of the algorithm starting to break down. So in the mixed precision version, we reverted the global sums to 64-bit arithmetic to try and protect against that, against floating point overflow. That had a negligible cost because the global sum is latency bound, not bandwidth bound. So that didn't really cost anything. And the sum is just for one number, so that's okay. It prevents the thing blowing up and falling over, but the slow convergence remains. It still converges far too slowly, and that's the same in single or double precision. So in the operations, they have a fixed iteration count. If you go beyond that, it pays the full start of the solver cost. So you might be able to do smarter things with restarts for the solver, but in operations, they want to know exactly how long it's going to take, or at least what's the worst case scenario and are they going to fit in the operational window. So if you go beyond a certain point, pay the cost of restart, they know exactly how much it's going to cost. So as long as that's not too bad, then they can do. So. But really, it's the ill-conditioned problem that arises from issues with noise in the horizontal wind field near the poles. So originally at lower resolution, the Met Office was doing the solve to only 10 to the minus 3, but then they started to see problems in other parts of the model from this numerical effect, and the tighter solver convergence kind of helped with that, but it has its own problems, as we shall see. So solutions to that, people are trying to do something called a polar cap to improve the numerical stability of the advection across the poles. Or we could try doing a multigrid solver, see later. So in conclusion, or to the first part of the talk, for the first solver, efficiency, speed, accuracy and stability are all important considerations for a numerical algorithm. Reduced precision can provide significant performance benefits, almost factor of 2, going to 32-bit. And the Euro in operations, the unified model in operations at the Met Office runs in mixed precision because it is almost twice as fast, but care is needed as the complex interplay between a round-off and other numerical errors can have effects, especially where numerical algorithms experience other problems, but that's not due to the single precision. It just means it's ever so slightly more susceptible to it. But okay, so we can do 32-bit and we can get good results. So that was the first solver. So as I said, the unified model, it runs on this longitude-latitude grid. It has scientifically good, very good performance and pretty good compute performance too. If we scale it up further, and let's go to a higher resolution, say 6.5 kilometer resolution, and then compare a local area model, which is the red patch, which doesn't have a pole, to the global model, which does have a pole, and then I sort of like scale them so they've got the similar amount of degrees of freedom to do the calculation and look at the scaling, then the blue, the local area model, scales pretty well, and the global model starts to turn over because it doesn't do so well, and the finger of blame is the longitude-latitude grid. So at 10 kilometers, at mid-latitudes, it's the grid spacing is 10 meters at the pole. So that's kind of where all the problems are coming from, and we'll stop the scaling. Okay, so I've come to this workshop quite a few times. I've given quite a few talks about gungho and Elfric. This is doing something in the Elfric model, so I've got a few slides, but I'm going to go through them pretty quickly because I probably said this before, but I'll do a quick summary for those who don't know. So the Met Office is writing a new model with a new dynamical core. The new dynamical core is called gungho. So the idea is we try and maintain the accuracy of the current model with a new mesh that doesn't have the pole problem. So for example, on the cube sphere, and to try and get the same kind of numerics they had before. So we can do this with mixed finite element scheme rather than finite difference. We can choose to have a different mesh. We could do triangles, although we are sticking with quads. We could choose to do different orders, although we are going to be lowest order. So we, instead of having staggered fields to try and get the sort of the same kind of C-grid effect, we have different finite element spaces that different fields live on, different spaces. And then we keep extruding the vertical. The discretization the scheme they use is sort of kind of inspired by the semi-implicit scheme they use in the so it's very similar to that. Okay, yeah, fine. Let's go on. We're going to run out of time. Okay, time stepping. It's what we might expect. So I'm just trying to get to the bit where I can show you some multi-grid plots. Okay, so we have this. So what is different is we have this. We construct this, a similar kind of a system, semi-implicit time-stepping scheme. We have this big outer system, which we actually solve with a GCR solver, and then, I'm going the wrong way, sorry. Okay, and then the pressure field itself, which we do the pressure solve as a preconditioner to the outer solve. So the Helmholtz system, we're going to solve using this geometric multigrid V cycle. Okay, so we do this by having this solver API where we have an iterative solver. A solver has a preconditioner and an operator and acts on vectors, and so we have this nice nested solver. So the outer solve is GCR. It operates on the bigger vector of the prognostic fields altogether, and then it has a preconditioner, and that preconditioner is the pressure solve, which we can either do as by CG stab, for example, or just do the multigrid preconditioner. Okay. Another way of looking at that is the time step. So in the same way I had a picture of the time step of endgame, it's kind of similar for the gungho Elfric model. Okay, so the profile I'm going to show you some performance results. What we're going to look at is the cost of the whole semi-implicit solver, which is the outer solve and the inner solve, and then look at the cost of the inner solve, which is the preconditioner to the outer solve. Okay, and then we can look at doing that either as by CG stab or with multigrid. Okay, so here's some initial results. It's running on a C192 cubed sphere, about 50-kilometer resolution. It's the baroclinic wave test, running on about 2,500 cores or 64 nodes in the Met Office XC40. This is all done with the Elfric Cyclone code generation system, so all the parallel code is generated automatically for both MPI and OpenMP. And you can see different ways of doing the solver. We could do Krylov subspace, different tolerances. We can do multigrid itself, or we could do multigrid just as a preconditioner and then do a bi-CG stab on top of that. Multigrid's much faster, and the number of levels you need depends on how big a time step, because to get the stability right. If we look at the residual after doing a Krylov subspace solve and before and after the multigrid V cycle, it looks like that a 3-level multigrid solver has reduced the residual by a factor of 10 to the minus 2. So that's the comparison I'm going to do with scaling, is comparing a 3-level multigrid cycle to the bi-CG stab to 10 to the minus 2. Okay, so we want to get as long a time step as possible. And so on that test, that was quite coarse resolution. So if I then increase the horizontal resolution to go to, say, 9-kilometer resolution, I've got to decrease the time step, but to try and keep it a kind of similar CFL factor. That gives me a time step of about 200 seconds. And I'm going to scale this out up to 1,500 nodes, the Met Office Cray XC40. Okay, so this is looking at strong scaling. So lower is better. This is a log plot here. So this is 96 nodes. This is 1,500 nodes. Multigrid is at least a factor of 2 faster than the Krylov subspace solver, so that's good because we like Multigrid. So the solid coloured sticks are Multigrid, the hash sticks are the Krylov subspace solver. They both seem to scale really well. Between 96 nodes and 1500 nodes, that's a factor of 16 increase in resource, out to about 55,000 cores. That's quite good scaling, but it's not the largest machine in the world, but it's still not bad. Oh, okay, right, okay, so we'll scroll through a few things. So one thing we're trying to look at the measurement is how much time do we spend doing the communication, and with the Cray Aries network, you get quite a lot of variation, so it makes it quite hard to tell sometimes how well you're doing. Most of the idea of doing Multigrid is to reduce the number of global sums, which we can see in red is lower than in yellow, but there is lots of variation there. Okay. That's cross image fetch. I'm going to go on. Of course, you could do Multigrid and mixed precision, which we intend to. And this is my conclusion. So, if you look at doing it, this is doing Multigrid and mixed precision in endgame. So we get both benefits of doing both. You can see the Multigrid looks like it's still scaling. For the unified model, the bit that prevents scaling is actually the advection around the poles, so the scaling doesn't look as good. But of course, the other thing we can do is then do mixed precision in Elfric, which we haven't done yet. But there, we'll be looking at doing the coarser grids in much lower precision to try and take effect of some scale effects. Okay, so in conclusions then, there's a complex interplay between accuracy, efficiency, the algorithm and implementation. 64-bit arithmetic is expensive. Lower precision can help us to do that. And the choice of algorithm, such as, for example, Multigrid, to reduce the amount of communication, in particular the global communication in this case, I haven't talked about redundant computation at all, is being deployed in response to architectural changes. So to go to extreme scaling, and again with this mixed precision stuff, it will be important for accelerators, which again I haven't talked to you about because that's a different talk. Thank you.
You wrapped it up pretty quick. So we have about 1 minute for questions. If somebody